Hi everyone, welcome back. In this video, we are going to work on putting it all together. And so we are going to work on constant pressure calorimetry and pulling in ideas of enthalpy and heat of reaction that we were talking about in the last video. Okay, so if we put this all together, we have that our heat of reaction, our delta H of reaction, is equal to the Q of the reaction, the heat that is released, divided by the moles. And we know about this Q, that we can experimentally determine this Q using calorimetry. And so if we can experimentally determine Q, we can get to this experimentally determining the enthalpy of the reaction. So let's do an example. Zinc metal reacts with hydrochloric acid according to the following balanced equation. When 0.130 grams of zinc is combined with enough HCl to make 50 milliliters of solution in a calorimeter, all of the zinc reacts, raising the temperature of the solution from 22.5 degrees Celsius to 23.7 degrees Celsius. Find the delta H of reaction, the enthalpy of reaction for this reaction as written. And then it tells us to use 1 gram per mole for the density of the solution and 4.18 joules per gram degree Celsius as the specific heat of the solution. Okay, to start off with, we're going to start getting ourselves organized. We know that we are doing calorimetry, but we also know that we are measuring the surroundings and not the system. And so we know that we can write that negative Q of the system, and we are using the negative because this is raising the temperature, which means it's giving off energy. And so that's a negative Q of the system is equal to a positive Q of the surroundings. And so I know that I can write this as negative Q of the reaction is equal to Q of the solution. And Q of the solution is equal to the mass of the solution times the specific heat of the solution times the change in temperature of the solution. So let's start finding these different variables. So mass of the solution. So the mass of the solution, we know from the problem that there are 50 milliliters of solution. So I have 50 milliliters, but I have to get this to grams. And this is where we use the density. So 1 milliliter is 1 gram. And so that's 50.0, I lost a sig fig, grams of solution. Okay. We also need to find the specific heat of the solution, which is actually given to us. It tells us to use the specific heat of water, which is 4.18 joules per gram degree Celsius. And then we need to find the delta T. Remember that delta T is going to be equal to the final temperature minus the initial temperature. And so this is equal to 23.7 degrees Celsius minus 22 I say it right and I read it wrong. 22.5 degrees Celsius, which is going to be equal to 1.2 degrees Celsius. So from here, we can put it all together. And so we know that Q of our solution is going to be equal to 50.0 grams times 4.18 joules per gram degree Celsius times 1.2 2 degrees Celsius. And so Q of our solution is equal to 250.8 joules. But this isn't exactly what we were looking for. We were actually looking for this enthalpy of reaction. And we know that negative Q of the reaction is equal to positive Q of the solution. And so Q of our reaction is going to be equal to negative 250.8 joules. But now we're not quite done, because we actually want to find delta H of the reaction, not Q. And so delta H of the reaction is going to be doing Q of the reaction dividing by the number of moles that reacted. So to think about this a little more conceptually, this is the energy that is released when 0.103 grams reacts. But this reaction is not for 0.103 grams. It's for 1 mole. And so what we have to do is we have to get rid of the contribution of the amount that we measured. And so we're going to normalize this out by taking this energy and dividing by the number of moles that actually reacted. And so to do that, I'm going to take the 0.103 grams of zinc, and I'm going to convert that into moles. And so the molar mass of zinc is 65.38 grams per 1 mole, which means that 1.58 times 10 to the minus 3 moles of zinc actually reacted. And so the delta H of the reaction is going to be equal to negative 250.8 joules divided by 1.58 times 10 to the minus 3 moles, which is equal to negative 1.59 times 10 to the 5th joules per mole. Okay, now a sloppy chemist notation thing. Many times when we write delta H of reaction, we don't use the unit per mole because of what we talked about, how it's per the reaction that happened. And so the stoichiometry plays a role here. I like to include that per mole. Oftentimes I will indicate what that is. But this is a notation that varies by video to video, book to book, way of teaching to way of teaching. So just keep this in mind. I try to keep my units really specific as to what I'm actually trying to present. But that's you've kind of got to learn the system that you're working from and the book that you're working from. Okay. So I'll zoom out so that you can see all of this. I hope this makes some sense, and I will see you in the next video.